So in the last few lectures, we talked about how to contain an object, both in terms of its geometry and the rigid body, which maintains its boundary and how it interacts with other objects. We also talked about the entity manager, which would then manage those entities and allow you to have a system by which objects sort of can be added to your engine and managed automatically for you, versus having to do each one by hand, such as setting the model matrix for a thing every single frame when you don't need to, right? So when we kind of explored this, we started to realize, well, if you have an environment with many objects, currently our entity manager is checking every one against every other one, and that can get quite costly. And in real-time games or in real-time simulation systems, more generally, you can very quickly get into trouble by doing the brute force approach. So if you have 1,000 objects, very quickly checking each object against every other object, right? That's a lot of checks. I mean, just simply put 1,000 times 1,000, that's 1,000,000 checks. And even with some of our best computers, doing 1,000,000 checks multiple times per second with what is a relatively costly thing. And sure, you can say, oh, it's not 1,000,000, we can cache and we can do things. But still, you get into a very difficult situation. And so how do you deal with these large number of objects? How do you get to that point? Well, so we're going to talk about that a little bit today. And let's get into it. So as we recall, two objects colliding in space, we can kind of break them down into their point clouds, so to speak, and then create a boundary around those point clouds. And that way we can rotate those boundaries and detect collisions against those collection of point clouds and kind of oriented in space, as we talked about before. Now, checking a collision between one object and another object is pretty straightforward. I don't think you can optimize that necessarily, but as we add more and more objects, now you have to do a collision between one, and then like one object against 9 others. But then if you want to detect the collision between every single object in this environment, you have to do 9 times 8 times 7 times 6, like 9 factorial checks, right? Because in theory, you don't have to check the 2 objects twice, which, by the way, is not always true. If you're doing a physics simulation, sometimes you do have to do 9 squared checks, because 2 objects may have collided and changed their state, and as a result of that, you now have to check a different update. But that's really dependent on how you design your system. But even here, say it's 9 squared, in the worst case scenario, that's 81 checks. 81 checks, like on a modern, even CPU, is nothing. But imagine like this scene from Minecraft, right? There are many objects in this scene that we have to check. In fact, we have to check against the ground, the bed, we have to check in objects in the walls and the chests and a lot of things. And so if we really want to be able to do it correctly, we need to start to come up with better techniques, better ideas, better approaches to effectively segment off objects. So like as we talked about right in the previous lecture, in theory, this is a kind of a good example. We're in a room, and our world may contain many objects outside of this room. But we kind of know that we're not touching any of them. There's like 0 likelihood, practically, of us touching any object outside of this room. And so by virtue of only looking in this room, we have taken what could be millions of objects and the need to detect collisions against them to only a handful of objects. So how do we kind of create this in a more generalized and straightforward way? So how do we think about this check? Actually, the example of a room is a very good way to think about it, right? If we have 2 rooms, objects in one room are almost guaranteed not to be touching objects in the other room. So again, you can kind of think back to the separation axis theorem. If we could somehow create a wall between two objects, then they're almost guaranteed, not almost, they are guaranteed to not be touching, right? And so if we can generalize this into effectively using a plane to cut our world, our environment, our universe into two dimensions, in this case the left and the right dimension, we can know for a fact that the Creeper and Steve are not touching one another because they are in opposite sides of this plane. We can kind of let them move around. As long as they don't pass this plane, we never actually have to look at their collisions. But what happens when they come into one another's space? So when the Creeper comes in and now they're both on the right side of the plane. Well, we can see these aren't touching, so all we have to do in this case is change the plane. So we can kind of deal with different dimensions, multiple dimensions, approach this in different ways. But as we add more objects, we run into an issue. Well, what now? What do we do now? Right, there's two objects on the B. Well, you can check collisions. You've cut down your checks by half at this point. But you can also add more dimensions. So one example of an approach is what's called a grid, right, where we can split up our entire world into effectively a grid, like a regularized grid, and we only check collisions between objects that occupy the same cell. So we would go through all of our objects and our cells and kind of do a cross-referencing of cells to objects, and for every cell that has more than one object, we check the objects in that particular cell, and we skip the empty cells. Now, actually, this is I think this is the way that Minecraft works. This is a voxel grid, ultimately, and so sometimes when you're doing grid calculations in voxel space, you can do some pretty creative and neat things. However, in a general sense, when your game is not a voxel game, to create the grid can be quite costly every frame. And so what more often you see is what's called a quad tree. So instead of splitting up our world into a grid, we only split it when we have to. So if you can kind of think about a quad tree as a data structure, and in this case it's actually a tree, right? But it has 4 quadrants. So your node gets split up into four, and it's top left, bottom right, whatever, or top left, top right, bottom left, bottom right, right? And in this case, the rule we're trying to maintain in the quad tree is that in every cell, in every node, we only want to have at maximum one or two objects. Ideally one, but one means we'll never have a collision, which as we'll see in just a second. So as we go through and we create our quad tree, we say, okay, we're going to divide our world into 4 quadrants. Now we have an object in the top left, bottom left, top right. We have 2 objects in the bottom right, so let's take the bottom right and split that up into quadrants. And now in that we have a object in the bottom left and the bottom right. So now we are guaranteed to only have 1 object in every cell, and we're done. So this is pretty easy. We add more objects. We don't have to change our system. And in this case, you can look at the quad tree data structure, and we don't have to do any collision checking. We are guaranteed that none of these objects are colliding. So what happens when we add a new object, right, in the quadrant where we're kind of on this edge, right? Well, we just, again, split it up further. So now we have, again, a tree where each node still corresponds to only 1 object. Now there's a limitation to this. That limitation being, well, what if objects are actually touching, right? There's no amount of, breakdown we can do to get them to the point where there's only 1 object in a cell. Well, there's a collision. We eventually do want objects to collide, and so in that sense, you do want to have set a kind of maximum depth to your quad tree. So at a certain point, we've gone down a certain number of levels, and at this level, we can say, okay, obviously any cell that has more than one object in it has a potential collision, and these are the cells that we actually run our collision detection on. So it's actually a pretty powerful thing. So even here, right, so ultimately this is sort of like checking every object against every object in the top left quadrant. Here we're only going to check the top left, bottom right, and then here again, top left, bottom right, and then and further and further and further, right? So it's pretty cool. We can increase the number of dimensions of the quad tree. We can do what's called the oct tree. The oct tree is effectively like a quad tree, except instead of splitting it up into two dimensions, we're going into the third dimension, which gives us 8, right? So we split it up into effectively a cube, and then cut that into smaller cubes and smaller cubes. And this can be very, very efficient for a large number of objects. There are other forms too. So we've been talking about axis-aligned separation, spatial optimization, and so there's what's called the KD tree, and the KD tree lets you split space in an arbitrary dimension, and this is, while more efficient, right? Because now we don't have to. We can actually find. It's almost like the separation axis theorem. We can literally find that plane that cuts our space into the most optimal organization of objects. At the same time, however, calculating this plane, calculating this dimension, can be quite expensive to do. As you probably know, right? You're going to do some form of an analysis of the objects, their positions, and so on, and it's less about min-maxing everything, right? Here, to create this kind of system, we're just operating on the boundaries of the quad tree and the objects, right? And on the axis-aligned aspects of them, unless you want to go a little bit, you can, again, the detection of how they fit and where they fit and what measurement you use is really up to you. But you can kind of see that ultimately we have a bunch of different rules we can use to get to this point, and with an oct tree as well. So with a KD tree, it's pretty hard sometimes to come up with this arbitrary axis. But this is the thing about the KD tree. Just keep in mind the way that this works is you come up with one axis and then an alternative axis that's usually perpendicular to your initial one, and so on and so forth. Right? You have like KD, KD. I think that's why it's called. I'm not sure what the KD stands for, but I remember implementing this when I was an undergrad, and you're constantly changing your axis, which can be quite expensive, right? But it's also made like recursive architecture. So yeah, that's really it for the explanation. So let's kind of dive in a little bit into the code. And again, I'm really going to talk more about the existing example, which is also what Alberto did in his section. So I won't be posting his. I might post his as well, just so you guys have it in case you want a little bit further, explanation. So let me pop open. This is the spatial optimization part 1. You have this in the repository, and let's just quickly run it and see what we get. Cool. So you can kind of see here what are a number of objects, and we're running at about 47 frames per second, which is important to note because we're not doing anything to ensure that frame rate, so we're letting the engine run as quickly as it possibly can. And so the frame rate is sort of a proxy for our performance, right? You can actually see in the top right, you can't see it probably in the video, but we're hitting about 22 something milliseconds per frame, meaning all the calculations that we're doing are taking us about 22 milliseconds to complete, and including rendering, including everything. And you can kind of see here that there are a lot of collisions. So here, for example, the collisions are highlighted in red. And keep in mind, right, we have our entity manager that we're adding all of these objects to. And you can see that we're detecting all the collisions accurately, even though there's a ton of objects, right? Even in situations like this where we have three objects overlapping. Now, you're looking at these planes, and you're like, well, what's the deal with these planes here? Well, this is an example of separating all of the objects into a number of different spaces. And so what we're doing, and I'll show you the code in a minute, we'll go through it, only objects on the left side of this plane are being checked against one another. Only objects within this plane are being checked against one another, and so on and so forth. So these planes are actually separating our world into multiple planes of where we're checking collision only in those scenarios. And I think it's important to note here, there are going to be situations where you will have some false positives, because from what I know about this example, there are some places we are putting objects into a plane based on its center point, not its bounds. If we were going to use the bounds, there was going to be situations where we have objects in both spaces, and that's not being done in this example. And if you find, so these spheres, these cubes are being placed kind of randomly. So we may find an example where one object is in one side and the other object is on another side, and there's going to be a lack of collision. But I don't see any examples of that here in this one. So if we run it again in the future, maybe we'll see a different thing. But great. So let's kind of see what's going on here and how this works. So let's pop open our app class, and this is all pretty straightforward. You probably already know kind of what's going on here. We set our camera, we added some lights apparently, and we set up our entity manager. Excuse me. And here we've decided how many instances we're going to have. So let's go down to 5 instances so we can kind of see what's going on. And we're going to basically sort of make sure that we have a square or whatever. And what we're doing is we're creating entities around this sort of spherical rand function with 34 units of radius. And what that's doing is it's basically what's called a unit circle random function. So imagine like a random number you get from 0 to 1, right? You can also get a random number across a unit sphere. And so it's basically a random number plugged into the Euler identity in the 3rd dimension. So it's not like that weird, it's just giving you a random point in 3D space. We get a vector, and we're creating an object. We're adding that entity. We're setting its position to a random position in 3D space, and we're setting its model matrix. So this is just doing all of that. And let's get rid of this code below, which I'll go into in a minute. And so now we have 5 objects that are going to be placed in a spherical thing. Let me actually get rid of those grids as well, so we can kind of see what's going on without anything. Cool. So now we can see we have 5 objects. They're clearly not going to touch. The likelihood of them touching is like 0. So let's go up to maybe 100 objects, and hopefully we'll see a couple of collisions. Okay. So here we can see that there's still no collisions. Let's reduce the radius a little bit. Great. So now we've got a few collisions. But our frame rate's quite high still. And keep in mind, I've removed these planes of detecting collisions. So we're not having too many issues there so far. So let's up it to 500. And now we're going to be checking every object against 500 other objects, effectively, well, nearly, approximately. And you can see our frames per second has dipped substantially. And this is a really good example because you can see there's a lot of collisions here, right? But even if I moved us back up to 34, like we had before, I probably will have a very, very low frame rate as well. a little bit higher. The reason it's a little bit higher is because the amount of code, like, as you recall, we have a bunch of early exits available to us in our collision detection algorithm. We can detect, if the bounding sphere doesn't align, we can quit early. And so we have less, as the sphere gets smaller, there's a higher likelihood of these objects overlapping. But you can see still at 500, we're like at 27 frames per second. It's quite slow. It's not a great experience. Or you can even see for whatever reason, the objects, the bounding volumes are not following. Funky things are happening in our engine because we're slowing down. So let's add let's add a dimension to the manager. So let's quickly look at our entity manager code since the last time. So we're familiar with all this stuff, but the piece that we're really interested in is the update function, right? So we've got a couple of new things going on. First of all, our entity list. We're going through our entity list and we're clearing the collision list. So each entity now has what's called a collision list, and this is a list of objects that it's colliding with. Let's take a look at the header of the entity and what's changed. And so this is, let's find it. Where is the? Here, no. Here, what is this doing? Oh, sorry, the rigid body. Right, sorry, the rigid body has our colliding list of all the other rigid bodies that it's touching. I think we had that from before, actually. So we're going through that, we're clearing all the collisions for each object for all of our entities. And now we're checking the collision against every other object. Cool. Now, here's a little bit of new code. So the entity manager code hasn't changed substantially, but the bit that we're doing, if we're not in the same dimension as the other object, then we return false. And this is actually the bit of code that allows us to segment the world into multiple dimensions. And how do we check that? Well, if we share dimensions, we can create these dimension counts. And this is what we'll talk a little bit about this in a minute and how we're doing it. If we have no dimension count, meaning there's no dimensions on either entity, then we return true because we're in the universe. There are no dimensions, right? If there's only one dimension that I'm in, right, then we just have to make sure that this dimension is the same dimension. And let's check out what this dimension is. And it's just a uint. Sorry, it's just a uint, the dimension that this object lives in. So in that way, we only have to check the value of the dimension, the ID. So if they happen to be in the same dimension, then great. We don't even have to check if the dimensions are equal. Now, if we have more than that, we are going to go through all the dimensions and ensure that the respective dimension lists are the same. So again, the dimension list is just a vector of uints, and we'll see how this gets set up in a minute. And this is kind of a convenient way. Instead of having to do the mathematical operation of figuring out on what side of the plane is this object, we simply we segment our world into these dimensions that this exists in, if that makes any sense. And we'll talk a little bit about this. This is kind of a brute force approach to creating a spatial optimization, but it works quite well for what we're trying to do. Great. So now let's look again at this code, and we're going to get rid of this. So we're going to undo these. And when I add the dimensions back, all right, you can see my frames per second is much higher. It's not 60 frames per second. It still takes a lot of frame rate to do all these checks, but it's okay. It's pretty good. But let's kind of see what we can mess around with here. So how are we adding this dimension? Well, here's the deal. So if we have a position of this object, we add, and it's less than 1, then we add a dimension, then we look at this area here, and we can add 2 dimensions. We have, if it's less than 17, then we add a dimension -1, 1. And if it's not, then we add a dimension -1, 2. The -1 is simply the index, so we're just adding it to the end of the list. And then same here, where when we add, we're just creating effectively these 4 dimensions at this particular point. And let's take a look at what this code does. So what we do here, when we add, well, first of all, let's take a look at our entity manager code, not our entity. So when we add a dimension, if our list is empty, then we just get out of there. We don't need to care, because we don't need to add any dimensions to an object. If we have more objects in there, then we're just looking for the index of the entity list, so to the last object that we're doing. So we're adding this dimension to the last object that we're in. And then we go into this code where we add the dimension to the actual entity. So now we're back into our identity code. And first of all, we check to make sure that this object is in the dimension that we're talking about. All right, the dimension list will ensure that we're in there, and by way of going through the dimensions and checking them. And then we're going to push back this dimension. This is kind of interesting approach, right? Like we're not really creating a check of any kind. We're simply sorting the objects based on these sort of imaginary lines. So in a way, you could even accomplish this with a map, right? Adding objects to, a particular bin inside of a map, or you can do it with. But this is basically just a way to determine that 2 objects are in this same dimension. If you look at this code here, you can kind of see that this will only hit one of these. We're either going to add it to dimension 1, 2, 3, or 4. These are effectively like unique IDs for these dimensions. And then when we're doing our entity manager update, where are we? In the update here, when we're doing the update, we are in the is colliding code of the entity. We are checking to see that these objects share their set of dimensions. So in theory, I could create I can add multiple dimensions if I wanted to. But we don't. For example, if I wanted to split by y as well. So let's quickly take a look at our performance here and see if splitting by y improves our frame rate. So right now we're at 46 frames per second. So now I want to create an additional set of checks. Instead of x, I'm going to do it by y. And again, keep in mind, I'm not looking at the boundaries, the bounds of the object. You could do that here as well. You could add multiple dimensions to an object if you wanted to, right? If it's sort of in one and the other, you could do that. And maybe we can see if we can fix that problem in a minute. And now we've added these 3 new grids. Let's do that. So axis, we're adding the z-axis, right? No, x-axis. X. Unfortunately, we've lost a lot of frame rate. Sorry. -17. Great, so now we've got, what was our last one? Oh. Okay. And then another thing we need to do here is we need to provide it with a unique ID. Because right now we're just adding it twice to the same dimension, and it's going to be confusing. We're going to have a lot of checks. So, cool. Now we've split it up into more dimensions. You can see that this actually hasn't helped us out too much. In fact, it's more expensive. But let's go only by the x at this point. So hopefully here we'll have the same performance as before. And so now we're only checking these objects against each other, the ones in the middle against each other, and so on. But what if we got rid of a couple of these dimensions and we just did it on x and y? We're kind of reproducing, in a way, the top level quad tree that we've been talking about. So here, if x is less than 0, then we're going to, that's going to be our first dimension. And then if x is less than, is greater than 0, that's going to be our second dimension. If y is less than 0, that's going to be our third dimension. If y is greater than 0, that's going to be our fourth dimension. We're just splitting it into by against the x and the y plane. And here you can see we're still not getting very much performance improvement. And one of the reasons is, you know, there are a lot of objects in these respective segmentations, right? We're not actually, because our scene is quite evenly distributed across these quadrants, and so we're actually still checking, we're only dividing the number of checks by 4 versus what we were doing before. So let's kind of do another experiment. And to be fair, like, this is sort of what a lot of the spatial optimization stuff kind of feels like when you're working on it. You try a bunch of different things for your particular application. Some applications do really well with grids. For example, Minecraft is exactly that, right? Other applications do really well with octrees, and some applications don't need this stuff at all. So let's go back to our original. What we're trying to do here is we're trying to improve. We're at 40. Let's see if we can, where does this break down? So right now we're better. We're back to 40 as we were before. Now, if I increase this to, say, 34, right? 34 is the radius of our sphere. So in that way, this is going to be equivalent to cutting space in half. And we can kind of see that when we do that, again, we're going to see a significant slowdown. Right? Because all these objects are being tested against all of these objects. You know, it's twice the number of checks. And so, yeah. What can we do? Well, what if we add an additional check? So if it's less than 5, no, let's do 13, or no, let's do 8.5, right? And then we do else if it's less than 17. Else if, and let's do a quick let's play with this, because this is going to be a little bit easier than constantly remembering to what's 17 plus 8.5? It is 25.5. Right. And then we're going to do the same thing here with positive. So let's see if segmenting it even further is going to help out our cause. All right, so we now need an 8.5, a 15.5, or 25.5, 8.5, and a 25.5, just to visualize it, right? And so what we're doing here is now we have 8 segmentations, and allegedly there should be way fewer calls. You can see now we have significantly less, like significantly better performance, but it doesn't look like any of the collisions are actually working. So what's up with that? Let's make sure our code is actually working correctly. Okay. Let me pause this really quickly to make sure that I'm not doing something silly. Okay, I was doing something silly. I was incrementing the index by 1 every time an object was, so every object was being added to its own dimension. So that was not going to help. All right, so now we've added 8 dimensions that each object is going to be added to. You can see now the collisions are better, but by adding a few more sort of segmentation checks and having to go through the list a few more times, we have indeed made our performance worse than just having the original number of things. I think what you'll find though is there is a sort of slope, this optimal number of divisions that you can get to, because the cost of subdividing your environment is going to have a performance cost. So in this case, it seems to be that the optimal number of sort of divisions is between 3 and 4 divisions for our engine. For us to be able to improve on that, we need to start thinking in different ways. And keep in mind, we're also in debug mode. In release, things like this will work significantly faster. Right? Like for example, if I go into release and I try to run this, I guarantee I'll have 60 frames per second. Very strong CPU. In fact, I could probably up it quite significantly. And here's where you'll start to see sort of the benefits of so you do have to kind of be a little bit wary of sometimes you have to be a little bit wary of your performance based on your computer and what's going on. You should run a lot of this particular stuff, like physics and collision detection stuff, in release mode, so you can really get a feel for whether or not it's working. Because oftentimes, a lot of the code that doesn't work particularly fast, it's due to be the debug build. So let's see where we start to crap out. So we're at 10,000 objects, so just going up by an order of magnitude. And here we might start to see problem. You can see how long it takes it to just generate all this stuff. And I'm stuck at 1 frame per second, so I'm gone. Everything's colliding. But if we go down to say 2,000 objects, right, and here we're at 22 frames per second. So you can kind of see we hit this sort of magic number at around probably is 1250 whatever unit entities. This is probably where we're kind of teetering around starting to hit the limitations, right, at 52. And what we can do here now is start to eliminate dimensions and see, well, if we remove the X dimension split, will we get any frame rate back? Or will we suffer more frame rate degradate, like fewer, less performance? And you can see actually no. In fact, sometimes it's a little bit painful because you realize that your spatial optimization is what's getting in the way of your performance. Like, for example, even without anything, my computer is able to hit 60 frames per second with this because of the complexity of the scene, the complexity of the geometry, yada, yada, yada. But if you're starting to get into like OBBs and expensive collisions, you'll start to notice there's a lot of things that that this will improve. So yeah, it gets a bit fickle, but either way, we'll start to see how this is really beneficial when we get into octrees next week. So hopefully this is helpful, and see you soon.